Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we were seeing so far is the closed Jackson network or Gordon Naval network. We have seen the basic theory and how it is different or how one can analyze that based upon our analysis of open Jackson network that we have done earlier, and we have seen an example. In that example, one thing I just want to point out here is this particular point, right. If you look at here, the traffic equation is given by this, right, in terms of rho I, but now it may be a little awkward to use the same rho I because we have been using this rho I for denoting the utilization factors. In this form, if you directly look at everything like properly, like it may be of that, but here it is not exactly equal to rho I of the actual utilization of the thing, but it is relative to that, because we are setting, for example, in this particular case rho 1 equal to 1 we are setting. Okay, we know that that may not be the case here in general for any network, but the rho 2 then we are obtaining in terms of that. Suppose if you set rho 2 equal to 1, then rho 1 would be some other value, right. So it is relative, right. So this relative thing will be taken care when actually you are computing in the G of M, when you actually computing this probability, like it will not make a difference. But if you want to interpret this rho as the actual utilization, that is not correct. So it can be less than 1 or more than 1, as you can see from here. For example, for certain values of P, Q, mu 1, mu 2, like this may even be more than 1 or less than 1, but what we are saying is it's just relative to this one which we are fixing it, right. That you have to keep remember. So this is not really the actual throughput or actual utilization, I mean throughput in the sense lambda i's corresponding ones, but this is the relative utilization is what this rho I. So don't ever interpret that as such is the actual. So that's why in some books like they use a different notation for this rho I rather than using rho I as we are using it here. But from the context for closed queuing network, you just have to keep this in mind that this is not actually the actual utilization, but it's a relative utilization is what we are having it here. Okay, let us look at one more example here, which is basically what we have in the text as well, which is the 2 machine 3 node closed queuing network, because this example, the example that we are going to see is going to come again and again. So just pay attention to this, because the remaining complete portion, whether this algorithms that we are going to introduce, we are going to come back to this example only, and we are going to talk about its implementation aspects. Okay, so that's why this particular example is simple. The previous one we have given because in a simple node situation, like you may have more different right. So for example, this particular network that we have, this is a single server queue. So for single server, one can have much more quite neat results for various other quantities like what we have had here. For example, these kind of quantities that we have had, you can write more. But for in general, it will be difficult to give that, but our concern is only obtaining the joint distribution, so we will confine to that. So here let us look at here, this is, we call it as a 2 machine 3 node closed Jackson network or Gordon Naval network. So assume that there are 2 machines which are in operating conditions and they need to be maintained in that operating condition at all times. Okay. So, they work for a duration of an exponential, they are in working condition for a duration of which is exponentially distributed with parameter lambda. After that they fail and call this operating node as node 1. Okay. So, there are two machines here which are there in operating, each of them independently works for a exponentially distributed duration with parameter lambda. Now, upon failure, a machine has a probability of R12 of being repaired locally. So, this local repair facility you call it as node 2, which has a single repairman and repair time follows exponential with parameter mu2. And when a machine fails, it can be repaired locally with this probability, okay, if it goes here, or it must be repaired by the again single specialist, which is what the specialist node is, what we call it as node 3 with the remaining probability, right. So, who works according to exponential mu3 distribution. Now, it may be possible that after repair being done locally, the machine may require specialist attention as well, and that happens with probability R23, or after local repair it will return to operation in operating node, which is node 1 with probability 1 minus R23. But after a special service completion, then it will always return to operation. So, it is R31 is 1. So, what we have here, we have 3 node, there are 2 machines, two number of customers is what quickly. So, either both may be in working condition or both may be failed condition with either node 2 or node 3, or one may be working, one may be failed, or both may be failed, all possibilities are there. And at node 1 there are two the servers basically here are the machines. So, there are C1 equal to 2, but C2 and C3 are 1 each in the remaining one. Okay. So, mu 1 here is actually lambda. So, if you depict this diagrammatically, so you have really in node 1 you have 2 machines which are working condition, which is with rate lambda, it will fail. Now, once it fails with probability R12, it go to node 2, which will take an exponential amount of time for the local repair. Then after which either it can move to node 3 for specialist repair, which will happen with probability mu 3, or it can come to operating node with 1 minus R23. Similarly, from here it can, from once a machine fails, it can also go for specialist repair with this probability, but after repairing in the specialist repair facility, the machine will come to operating condition. So, this is with probability 1, you have this node. So, this is what we had here. Really, like there is no queuing happens here, just for the completion sake we have put this, but as you see there are 2 servers at maximum of 2 2 servers are there and 2 machines only, 2 customers only. So, both can be accommodated here, whereas here there could be a possibility that one is being repaired, the other is waiting for repair, one is being repaired, other is waiting for the repair, but here it will be both. So, there is no queue, right, but we are just depicting it because we are allowing it, no problem, but there is no queue happens there actually, right. This is what is the model. Now, what we have to do, the steady state joint probability distribution is essentially this, because 1 over G of 2 is the normalization constant, and this is corresponding to the first node, which is MM2. So, for MM2 the factor will come in is this rho 1 to the power n1 divided by A1 of n1, where A1 of n1 is 1 for 0 and 1 for 2 specialized ones, A1 of 2 equal to 2. So, if you specialize to 2 customer the network, this is what will happen with the 2 servers, and for the other 2 nodes or single server you will have the corresponding factors here. So, this is G2 will take care of all the total possibilities. Okay. So, we must find rho I now from this set of traffic equations, and here the routing matrix is this as we have described, right. From node 1 it will go to node 2 with probability R12 or node 3 with probability R12. From node 2 it will go to either node 1 with this probability or node 3 with this probability. From node 3 it will go to always node 1, which is with this probability 1. So, this is what is the routing matrix. You just have to write down the routing matrix corresponding to that. Then this equation, right, would be set of these 3 equations, right. We know these equations are linearly dependent, so we have to set one of them equal. So, we for conveniently we set rho 2 equal to 1. Okay. Now, if rho 2 equal to 1, then from this equation, then rho 1 is simply mu 2 over lambda by lambda times r 1 2 is what you will get here as rho 1. Now, you put rho 1 rho 2 in the third equation, right. So, rho 1 and rho 2, rho 1 and rho 2 in the third equation. So, you will get this as the rho 3, which is equal to this, which can be simplified to this. So, this is what is the expression for this rho 1 rho 2 rho 3. Remember, like this rho 1 rho 2 rho 3 need not be less than 1, it can be more than 1 or greater than 1 or any value it can take. That is what it will come out to be, because there is no guarantee that it might come. Okay. So, once we have this, then we have the steady state solution of the closed network, which is given by this, where g of n can be obtained by summing over this quantity over all cases for which n 1 plus n 2 plus n 3 equal to 2, because there are total 2 customers overall in the network. So, there are 6 cases possible here, which is either both will be there in node 1 or node 2 or node 3, or one each in node 1 and 2, 1 and 3 and 2 and 3, right. So, these are the cases. Now, like if I evaluate these quantities for each of these cases and I sum it up to express what is going to be my g of n here. So, I can obtain the normalization condition appropriately, right. So, that is how you handle this, right. So, you have for this network. Now, for illustration purpose, for for easy understanding and then going forward as well. So, let us take some specific values for the parameters. Lambda equal to 2, mu 2 equal to 1, mu 3 equal to 3, r 1 2 is 3/4, r 2 3 is 1/3. So, 1 minus r 1 2 is 1/4 and 1 minus r 2 3 is 2/3, that comes automatically, because as you see here we said that this matrix will be a stochastic matrix. For a closed network, this must be a stochastic matrix, that you have to remember. Then, since we have already obtained rho 2 equal to 1, rho 1 is this, rho 3 equal to this, which gave you this. Now, if I substitute all these values that I have here, then it boils down to this, where a1 of n1, as we have said here, is 1, that a1 of 0 is 1, a1 of 1 is 1 and a1 of 2 is 2. That is what the 3 quantities that you have depending upon what is the value of n1 here, right. So, and n2 of course. So, this is what once you get that you will get the thing. So, now g2 you can compute in a naive computation manner, like for each possible values, because you have different states, right. 2 0 0, that will give you this term, this is 0 2 0, this is 0 0 2, this term is 1 1 0, this term is 1 0 1 and this term is corresponding to 0 1 1. So, you can compute for each of this to get the sum. So, if you plug it here, then you have determined completely the distribution of this. Now, if I compute for each of these 6 states that are possible, this is what is turning out to be the corresponding joint probability distribution that you have here. Now, once I have this joint probability distribution, now like if I want marginals, I can obtain. If I want other quantities, whatever I require with respect to this, I can obtain from this distribution. So, once we obtain this distribution, then marginals, mean number in the system, everything can be obtained from this. And okay. But there are certain facts, I mean, if these were the parameter values, then there are certain facts that you need to look at with respect to the values, as you always look at, right. You see here this probability is very low, which means that only about 10%, less than 10% of the time both the machines are in working condition, right. And about 43% of the time the machines are with local repair, right. There is only one repairman, but this much it is there, I mean with state 0 to 0, which means both the machines are at local repair. So, there must be something you need to do with respect to this. This is the kind of insights that you have to do, where there is a problem and so on. If you want to look at it, you can look at from here. So, here there is not much problem because much less is going here, but that might be possible because of this 3 by 4. That is why it is getting clogged here, right. The system is getting clogged here in a way, right. But if this is decreased, then possibly this will decrease and this might be increased. But so you can balance out and you see how it is going on. And this also tells you that the problem with node 2, right. Wherever that is there, you have this higher probabilities, right. So, that is your, and at least one machine available if you want to look at it, just 45% of the time. So, about 55% of the time not even one machine is in operation. So, performance, if these were the parameter values, is not up to the mark and you have to decide now how to improve. Okay. So, this is with respect to this particular values, but what we are looking at is that how we are getting this and how we are implementing this, right. So, that is what then you are obtaining it here with respect to this particular example that we have here. Okay, fine. So, this is what is done. This example we will keep coming back, and remember this particular slide where we have the distribution as well as the probabilities given. So, this part is what then we will come back again and again. Okay, fine. Now, in the previous example, because it was 2 node, the computation of the normalization constant, which is basically this g of n, was relatively easier. In this case as well, because there are 2 customers only, and even though there are 3 nodes, things were not that difficult, a naive computation can give easily. But in practice, this is not that easy to compute. The main computational difficulty when you are trying to obtain the joint distribution of the number in the system in the whole network is connected with the evaluation of this g of n. Okay. Up to this the process is the same. Now, g of n, in this way of evaluating by enumerating all such possibilities, here it so happened that n1 plus n2 plus n3 equal to 2, it gave rise to only 6 states. So, you can evaluate all 6 states what is going to be, and then you can compute this g2 directly, right. But it may not be that simple in general. So, since the joint probability distribution determined in terms of this normalization constant g of n here, okay, we generally use the notation n, g of n. So, in the examples that we have considered, this naive brute force approach of calculating was easy, but that is not the case in general. For example, for large n and k, mainly the number of customers are large and also number of nodes, then there are many possible ways in which one can allocate this n customers among the k nodes. Actually, it is n plus k minus 1 choose k minus 1 ways, which is roughly of the order n to the power k minus 1. So, you can imagine if n is large or k is large, what would be the number of states that might come. And also these calculations are prone to numerical errors, accumulating numerical errors as well. So, people were looking for an efficient way of computing this g of n, because this is what is the main crux. This once you compute g of n, after solving the traffic equation, once you are basically determine rho 1, rho 2. This is, as we said, that is relative utilization, it is not the actual utilization. But once you computed that rho 1, rho 2 and so on rho k, then it was only the question of how to compute this g of n. How do we compute this efficient way? One such algorithm was given by Buzan in 1973, so which turns out to be an efficient algorithm to compute g of n, but it does use a recursive scheme to compute this g of n. In a single server case, you can easily see that it is performing that nk multiplication and nk addition. So, you can see how much improvement that can make. Again, we stress that it is very useful for larger values. Smaller networks, smaller values of n and k, we have seen that it can be done very easily, it is not very complex, but for large network this is. So, what is this algorithm is, that is what we will see how we can compute this g of n. Okay. So, let us call this factor which is the product factor, in the product form solution, whatever is the product term, let that factor be called as fi of ni. So, here we are writing it for in general for a multi-server case. If you specialize this algorithm to single server case, then you can get some more expressions, some more neat results as well for certain performance quantities of interest as well. Okay. But since that was not our interest mainly, so we restrict ourselves to, or we take it in the generality of multi-server case. So, we retain this factor. Okay. By the way, this algorithm is also called as this convolution algorithm, okay, because the factor coming out is basically convolution form, it will come into this case. So, we know this fi of ni is this, where a of ni either this or this, which is what we have seen the simple example as well. Now, once we write this, then the normalization constant is basically, you can write as summation of this such that f1 of n1 into f1 of f2 of n2 and so on, which is what this product is, right. So, that is what is the normalization condition. Now, what you do, you define an auxiliary function which is gmn. Okay. Now, what is that? You look at this function carefully and compare with this, what does it mean here? It is summation of n1 plus n2 plus nm, which is equal to n, and product of I is equal to 1 to m fi of ni, which is basically, you can see here what is that? You have k nodes and total of n customers here. So, here you can think of this as m nodes and n customers. Okay. That is what this function gives you. This auxiliary function gmn is a quantity which is similar to this g of n, which is for k nodes and n customer here, which is this is m nodes and n customer, this is what you have. So, that is what we are writing it here. This is m nodes and within bracket is number of customers, just like here we have writing it as number of customers as within bracket for capital G M. Now, if I put this m as k, so the sum will be up to n plus n k, and which is equal to capital N, then I will get back this g of n. So, basically in this auxiliary function, if I take g k of capital N, then that is what is going to give me this g of n, right. So, I am defining this auxiliary function, and for particular values of m and n, if I take, that is k and n, then I am going to get back, or I am going to get what I wanted to compute, which is the normalization constant. Now, what we will do is that the algorithm is basically aims at computation of this in a recursive way. So, that is a scheme that we have to figure out what is the recursive scheme that we can have. Okay. So, take this gm of n as we defined here. Okay. Now, take the last one, this nm, you fix it to be some value I. Okay. You can fix it at some value I. So, I can change the product from j from here, because I am fixing that I there. Then what will happen to this sum? So, this is summation of n1 plus n2 plus n of m minus 1 plus that nm, I am fixing it as I. This is all equal to small n, and the product is j to 1 to m of fj of nj, right. That is what I will have. Now, since I am fixing this I, okay, and this I could be anything between 0 and n, right. So, all possibilities I have to write it, right. So, if I fix this I, then that is what you have here. Then what I can do, so that means I can take out the mth quantity from here, I can write it outside, that will be fm of I. The remaining product will be j equal to 1 to m minus 1 of fj nj, and the sum of n1 plus m2 n m minus 1 would be equal to n minus I, because I you have assumed it to be in the mth node, right. You have m, totally this is m nodes n customer, out of which if I allocate I customers to the mth node, the remaining n minus I customers will be there with between the remaining m minus 1 nodes, and that is what will give you this. Now, this quantity the one which is in this bracket is basically g of m minus 1 of n minus I customers. So, which is in m minus 1 nodes n minus I customer. If I have this quantity gmn, this is what you have here. So, basically what I have gm of n, okay, is basically I is equal to 0 to n of f m I and g m minus 1 of n minus I. Okay. Now, from this we can observe that G1, when there is only one node, this n would be exactly same as f1n, right, for all 0 to n, and Gm of 0, right, if there is 0 customer, then this function is 1 for all 1 to k. This is the starting condition for the algorithms. Okay. So, this is the starting condition for algorithms. Now, once I have this as the starting condition, right, Gm of 0 I know and G1 I have. Now, once I have G1 here, then G2 of n, right, G2 of n would involve, so G1 of n I am giving completely here, right. So, that is with one node what would happen is basically f1 of n. There is nothing peculiar or great about that, and once I know all G1 for all points 0, 1, 2 up to n for all number of customers, basically if it is in one node what would be this quantity, then G2 of n if I look at it, if I see that this will be int of G1 of something, right, n minus I. If I fix I here, then n minus I is what you get. So, G2 would be in terms of G1, then G3 will be in terms of G2 and G4 will be in terms of G3. So, you compute this recursively using this recursive relationship, right. So, this if you go and the algorithm will terminate when you reach with k nodes, right, because you have k nodes is what you have it in mind. So, starting from G1, G2, G3 and you keep continuing to compute up to Gk, and once you get that, then your algorithm will terminate and you can obtain the quantity here. Okay. So, this way of computation is very efficient for large networks, as one can see, but we will see simple example only where you may not really see the power or utility of this algorithm, but in practice this is quite useful for large networks, and there is nothing like one node to one customer to customer network, which is much easier to even observe. You do not really need a lot of whole stuff of this kind of queuing analysis to be done, okay, and only when you have large number of system that you have here. Now, in addition, these functions also helps us in calculating the marginal distributions as well. So, say for example, if I want the marginal distribution of the ith node, which is this, now let us call Si to be this sum without this ith term in the middle, right. The rest of all ni's is what you denote it by Si, okay. Then Pi of n if I want, then I will take this joint and I have to look at sum over all remaining possibilities, right, n1, n2, ni minus 1 and ni plus 1 and nk, their sum equal to n minus n, right, is what is a possibility I have to enumerate to get Pi of n. So, this one is essentially this one I can write straight away, but the sum is now. So, the Si notation we are utilized just because we do not want to write this long expression here. So, we are using the notation Si, that is all. Now, in this if I take the the ith one out, right, because I am keeping this ith one only out, then I will get this as the expression, right. I could have even written here j without much, does not matter, right. So, this is Fi of n, the ith one if I take it out, then j not equal to I will get the remaining ones here, okay. In general, this quantity is little cumbersome to compute, but conveniently if I take the last node, that is for node k, this expression is very simple, that because then you can write instead of the j not equal to I, this will be only the last one you are leaving it out. So, it will be like this. So, that can be written easily as g k minus 1 of n minus n. So, one can write for the kth node this as the quantity, But if you want to find other marginals, one way is to permute the nodes, so that whatever the node that at which you want to compute the marginal distribution becomes node k. But if you want at every other node, then that becomes difficult, because this involves some modifications to the function gmn as well, because once you change the node, things also will change in this as well. Okay. If only one marginal distribution, then you can set that as the last node and then you can do the computation. But if you want more than that, then this way of doing it would be difficult, but there are efficient ways, but we are not getting into that. So, but there are efficient ways, even with modification to this process, that one can get the marginals. But what is the crux here, or what is the thing that you are taking away from here, is that this quantities, the auxiliary functions that we defined in the convolution algorithm or Boolean's algorithm, also helps us to compute the marginal distribution. That is what you have to take. Okay. Fine. Now, let us see how this algorithm can be implemented for the example that we just did, the 2 machine 3 node model. Okay. 2 machine 3 node closed network, the illustration part we are revisiting. So, first we have to find the factors fi of ni. We have defined fi of ni to be this quantity. So, we have now like all these things, all these parameters values are there, and we know what are these quantities. So, this is what is this quantities that you may have in general, right. So, this is f1 of 0, we just have to plug in the values there and see that this computation, and because I set row 2 equal to 1 and row 1 I obtained in terms of row 2 and row 3 you obtained in terms of this. This will play a role in determining what are that quantities, that row 2 to the power n1, n3 and n2 and so on, right. So, from there I can obtain f1 of 0, f1 of 1, f1 of 2. This is the for the function f1 of n1. Similarly, f2 of 0, f2 of 1, f2 of 2, because 0, 1, 2 are the number of customers that is possible here. Now, f3 of 0, f3 of 1, f3 of 2 you can obtain it. So, once you obtain this, then your algorithms can start. Now, if I look at, because in this algorithm that this is required for all values of this I, because if you want recursively m, for each m you want, and also for each m for all i's you want. So, that is what the starting you have to compute before you initialize to this value, then apply the recursive step. That is all you would do. Okay. So, the recursive step, since you can directly go to what you wanted to get. We wanted to get G2, which in this case would be given by G3 of 2, right. Now, G3 of 2 would involve F3 and G2, right. So, F3 of I, G2 of 2 minus I, which I is equal to 0 to 2 here, because there are customers is number of customers is 2 here. So, this is 2, fine. So, this is what you have here. So, that means I is equal to 0. So, F3 of 0, G2 of 2 plus F3 of 1, G2 of 1 plus F3 of 2, G2 of 0, right. I have already obtained this F function. Now, what I need to know? I need to compute, because I know that G3 will be in terms of G2. So, G2 of 0, G2 of 1, G2 of 2 I need to compute. G2 of 0 anyway we know from the initial condition, G2 of 1 and G2 of 2. So, G2 of 1, but now it is G2 of 1. So, this will be in terms of F2 and G1. So, F2 of 0, G1 of 1, F2 of 1, G1 of 0, and G2 of 2 will be 3 terms like in this particular case, right, like what we have it here. Here also you will have 3 terms here. And the starting condition, as we know, is G1 of 0, which is also F1 of 0 equal to 1. Okay. So, what you have here, G1 of n is F1 of n and Gm of 0 is 1, right. So, Gm of 0 is 1 for m1, 2, 3, and G1 of n is basically F1 of n. So, F1 is basically 0, 1, 2. So, accordingly G1. So, G1 you will get from the starting condition, Gm 0 you will get from starting condition, then once you get G1, then G2 recursively you compute for G2, then you compute for G3 and so on. Okay. Okay. So, if you do the calculation now, so you can go reverse. G2 of 1 is this, just you have to plug in the value. G2 of 1 is F2 of 0, G1 of 1. G1 of 1 is 2 by 3, F2 of 0 is 1. So, you get 1 into 2 by 3 plus 1 into 1, which is 5 by 3, and similarly for G2 of 2 you have these 3 terms, F2 of 0 which is again 1, and G1 of 2, right, G1 of 2 is 2 by 9. So, the first term will be 1 into 2 by 9 plus this, so it will give you 17 by 9, and once I have these 2, then I can plug in here, because G2 of 0 I am getting it from here. So, G2 of 1 and G2 of 2 I can get from here, I can substitute here to get my G3 of 2, which will give me, this is effectively equal to the water quantity that you are looking for, which is G of 2, right. You remember, this is what we had obtained earlier also when we did the computation, right, naive computation here. Okay. This is a very simple example with the 2 customers. So, the algorithm may not have helped to get lesser number of computations, just that illustration of the algorithm how it works, but the efficiency will be evident when you consider very large networks. Okay. Now, let us, the tabular form we have kept it here just for easy reference and understanding of how this algorithm works. Okay. So, this, the first column is what is given by G1 of n, right. This is the one, G1 of n is what is given by the first column. This is given by the initial condition, right, which is equal to simply F1 of n. Once you compute that, then you will get this one. Similarly, this one Gm of 0 will give you this first row, which is also coming from the initial condition. Then the rest of the table you have to start filling. Okay. Now, you know that this 5 by 3, if I look at here, it is here, it involved this 2 by 3 and 1, which are basically these 2 quantities. So, these 2 quantities will determine this, and for determining this, all these 3 quantities determined this. Okay. If I have more, right, then these 4 would determine this 4th quantity. 5th quantity, if I have this, all 5 quantities will determine the 5th quantity here, if I have something more. But this first column, first row will given by the starting condition, then you have to start filling these elements one by one by computing with this. So, you have to multiply this appropriately, right. So, this is, as you see here, right, this 1 is multiplied by with this 1, and this 2 by 3 is multiplied with this 1, right. That is what, you know, that is coming from the other ones, f function, f2 function, right. So, that is what you get here. So, basically how you will fill it up, you will have this to start with, then you start with this involving these 2 and the corresponding f, these three and the f, like this, you know, you will start filling up this table. Once you get this, then you will get this column and this column. Remember here, we need not compute this, right. If our final objective is to compute the last element, which is the g of n, at least for the last column, you need not compute the intermediate values, but the last one directly you can use all the previous column value, then you can compute this. That is what pretty much we have done, but this column also, this entry also we have computed in this particular case, and we have plugged it here. The reason that, you know, if it is good that you have the complete table is that the performance measures are, if for example, if these are a single server network, I mean, you can write down nice expressions for the utilizations and other performance measures, throughput and other performance measures, everything in terms of these m's. Recall, in one of the previous example, we wrote certain probability as g m minus 1 by g m sort of thing, right. So, this is sort of your g m, g n, and this is sort of your g n minus 1, right. So, that is what, in such situations these entries may be of some help, but if your interest is only the final entry from the previous column, you can directly get here and then you can stop as we have computed here. Okay. So, this is what is the algorithm and how one can work it out. Now, once I compute, so this is basically the convolution algorithm or the Buzan's algorithm is only for computation of this normalization constant, which will be plugged now into your usual expression for the joint probability distribution, and once we have the probability distribution, then you can get the other performance measures of interest, right. So, go back, like if you have seen, this is what we are computing it through that algorithm rather than computing it in this manner. Now, once you plug it here, then this expression will give you these probabilities, and then further things will go further. Okay. So, that is what you have it here. Of course, a little bit more can be said if it is everything is single server or just specific cases, but our objective was to introduce this algorithm in computations, so that you can, if you want interested more, that you can explore yourself from here, from this point onwards. Okay. We will stop here, and then we will come back with another algorithm in the next lecture. Thank you. Bye.